Welcome and thank you for joining. In this lesson, we'll explore the exponent laws. Now, this is a lesson prepared for grade 11 university preparation, but practically this concept has been covered in grade 9, and we are quickly reviewing it as we make progress into simplifying more complicated exponential expressions. So recall that in order to operate with exponential numbers, it's not the same as operating with regular numbers. So for example, if you have 2 and 3, you can add them very easily by combining 2 and 3, it gives 5. But if you add 2 to the power of 3, say, for example, and you are adding to this 4 to the power of 5, there is no rule that can help us combine 2 and 4 and 3 and 5 together. And the same thing applies to having a negative here instead of a positive. So even if we had, for example, 2 to the power of 3 and we're adding, let's say, 2 to the power of 5, still there is no rule that can help us to either add or subtract these two exponential numbers, even when the bases are the same. So what we're trying to say in here is that when we operate with exponential numbers, we have to follow special rules, and addition and subtraction is not as straightforward. So the main rules that we'll focus on are what we call the product, the power, and the quotient laws. So these are the three main laws in operating with exponential numbers. Now, the product law helps us multiply two exponential numbers, and it goes like this. So the product law is a to the power of m multiplied by a to the power of n would be equal to a to the power of m plus n. As you can see, in order to multiply two exponential numbers, their bases must be the same. If they're not the same, they cannot be added, and their powers will add. As an example here, I'm going to bring 2 to the power of 3 multiplied by 2 to the power of 4. So in this case, then we're going to say that 2 to the power 3 breaks down into 2 times 2 times 2. 2 to the power 4 is multiplication of 2 by itself 4 times, and the answer would be 2 to the power of, so we just count the number of times 2 is multiplying itself, and we get 2 to the power 7, and that's exactly coming from that is coming exactly from adding 3 and 4 together. So the next law is what we call the power law that helps us bring exponential terms to a specific power. So if you have a to the power of m, you want to bring it to the power of n, then we will multiply the exponents and keep the base the same. Now, as an example here, I'm going to bring x to the power of 3 raised to the power of 2. So x to the power of 3 to the power of 2 means that x to the power of 3 is multiplying itself twice. So when you multiply x power 3 by x power 3, you get x to the power of, we already know how to multiply 3 by 3, which is x to the power of 6. So as you can see, number 6 here will come from multiplying the two exponents. Now, very important to remember that x doesn't get multiplied or changed in any form. You just keep the base the same. And same in addition. So you multiply in multiplication where we add the exponents. So when you multiply two exponential numbers, we just operate with the powers. The base stays the same as it was in each term. Now, the quotient law helps us divide two exponential numbers. And if we are dividing a to the power of m by a to the power of n, then we're going to say that it's very important the bases are the same. Otherwise, we can't even divide them. And the answer will be a to the power of m subtract n. As an example here, we're going to take a look at 3 to the power of 5 divided by 3 squared. So when this happens, then we're going to have 3 to the power 5 written as 3 times 3 times 3 times 3, 5 times, divided by 3 times 3, only 2 times. And as you can see here, the first 3 will simplify the second one here, the second will simplify the second here, and we're left only with 3 times 3 to 3 times 3, which is basically equal to 3 to the power of 3. And this power of 3 comes exactly from subtracting 5 minus 2. Now, besides the exponent laws, there are some other rules that we often use in simplifying exponential expressions that we call exponent properties or properties of exponents. So they are derived by these main laws, but they are shortcuts, or they are simpler and very practical to use. We use them very often in simplifying expressions. So the first one is what we call the distributive property. Distributive property consists on the fact that if the base has is expressed as a product of two numbers, then the power will apply to every part of the base. And a times b to the power of m is a to the power of m times b to the power of m. So as an example here, we're going to take a look at a times b times c to the power of 4. And that will be equal to a power 4, b to the power 4, c to the power 4. So the negative exponent property, a very important property we have practiced heavily in grade 9, is when the exponent is negative, we can convert it to positive. And remember that final answers must be expressed with positive exponents, so most simplified and positive exponents. So this rule has been used very often. And when you want to change the exponent from negative to positive, you just flip this over, and that automatically changes the exponent from negative to positive. And similar to this, if you have a to the power of m equals 1 over a to the power negative m. So if this exponent is negative, it can turn positive by bringing this up in here, and vice versa. So when you look at this, and I can just very quickly explain this with a simpler explanation, I would say. But if you have 1 over a to the power negative m, you practically have, let's say, a to the power of 0, which is 1 over a power negative m. So when you apply the quotient law, this becomes 0 minus negative m. So 0 minus negative m, which makes this positive m. Now the zero exponent. So zero exponent is when a to the power 0 would be equal to 1. And I'm going to add a couple of more rules in here. Now remember that a has to be different than 0. The reason why is because if we have a to the power of 0, you can look at it as a to the power of m minus m. Okay, so let me just quickly explain this here. So if you have a to the power of 0, that's m minus m. So when you have subtraction, that means that there would be division of two exponential numbers. So you see how you end up with the same exponential number here that simplifies to 1. Now imagine if a was 0 though. If a is 0, then numerator will be 0 and denominator 0. So, and that would end up being 0 over 0, which is undefined. That's why the rule specifies that a has to be different than 0. So the next rule is the base of 1. You raise number 1 to any power. It's not going to change its mind. It's going to stay equal to 1 because it's a repetition of multiplying 1 by 1. And last but not least, 0 to the power of m, that would be equal to 0 no matter what. Now, let's take a look at some examples. So what we have in here is 3a squared b minus 2a cubed b squared. So we'll multiply the coefficients together. Okay, so I'm going to show the long way in our first example. And obviously, we want to cut the ways a little bit shorter. And we have a squared in here and a cubed in here. So we're going to bring them closer to each other so they can see each other and we can see them, the terms, so when we simplify. And then we have the b's as well. And let me just highlight them. And we're going to make the b's blue. Why not? Okay, and the b is squared in here, so I almost forgot. Now, we have 3 times negative 2, negative 6. Here you have multiplication of a with a cubed, a squared with a cubed. That will give a to the power of 2 plus 3, 5. And b to the power of 1. Remember, when the power is not visible, it means that the power is 1. And 1 plus 2 equals 3, and that would be our final answer. Now, let's take a look at the next example. We have m to the power 3 to the power 4. This looks like the power rule where we have to multiply the exponents. So that would be m to the power of 12. Next, we have negative 4p3q squared to the power of 3. Now, one of the mistakes I notice people often make is they bring all the variables to the power of 3 and they forgot about this poor little coefficient. This is inside the brackets. This is also brought to the power of 3. And please make note of it if you ever make this error. So we have negative 4 will be raised to the power of 3. Oops. So to the power of 3. And then we have p cubed also raised to the power of 3, and then q squared also raised to the power of 3. Obviously, you can cut the way shorter. This is not a difficult question. So negative 4 to the power 3 is negative 64. Now, p cubed to the power of 3 is p to the power of 9. And then q squared to the power of 3 is q to the power 6. And this would be the final answer. Now, let's take a look at some more complicated examples. So this is where things start becoming a little bit more fun. So we have the power of a quotient. Now, one of the mistakes that it's very easy to make in this case is as soon as we see this number 3, exponent 3, we rush into distributing this to every part of the expression inside the brackets. And there is nothing wrong, like mathematically speaking, there is nothing wrong with it. But practically speaking, this is going to complicate the solution. Now, when I said mathematically wrong, like I use this term a little bit loosely because we also have to remember the BEDMAS rule. So the rules are made to simplify the process, and sometimes there are more ways to solve a problem, so some longer than others, but the rules will guide us to finding the right answer in the fairly shorter way. Now, BEDMAS suggests that we take care of brackets first, and you see a set of brackets here, which means that we have to check and see if we can simplify inside the brackets. So what I see inside the brackets here is, or are, I should say, the numbers 6 and 8 that can reduce to 3 over 4. So they're two even numbers reduced by 2. Now, x to the power 5 doesn't have anything to simplify with, so it's going to stay here as is. And y3 over y squared will be y to the power of 3 minus 2, which is 1. And then the power of 3 will stay outside. So once we have completely simplified the inside brackets expression, we can bring the power of 3 in. So we're going to have 3 to the power of 3. And then x to the power of 5 to the power of 3. Obviously, you can follow a shorter way, so you don't have to show the steps all the time, the way I am right now. So that's for the purpose of explaining things at this moment. And 4 to the power of 3. So remember the equal signs here. And we have 3 to the power of 3, which is 9. 4 power 3 is 60, okay. 3 to the power 3, which is 27. And 4 to the power 3, which is 64. X to the power of 15, and y to the power of 3. And this will be the simplified expression. Now, normally we would state also the restrictions in these type of expressions when we have the variables in the denominator. And we're going to go back to where we were here without the denominator simplified. And we're going to say that the restriction here is that y cannot equal 0. Now, in the same way, we're going to operate with the next question. You can try this on your own because it's not that difficult. It's very similar to what we just did. So always simplify inside the brackets. The coefficients are not simplifiable, so negative 2 over 5. Now, x to the power of 3 can simplify x to the power 1 to give x to the power 3 minus 1, 2. And y to the power 6 divided by y squared will give y to the power of 6 minus 2, which is 4. And the power of 3 will stay out. And we're going to have now negative 2 over 5 to the power of 3. So negative 2 power 3 and then 5 power 3 here. Now, x squared will be to the power of 3, and y4 will be to the power of 3 as well. And let's see what we have cooked here. We have negative 2 power 3, which is negative 8. X is to the power of 6. Y is to the power of 12. 5 to the power 3 is 125. And this is the final, most simplified answer. Now, we're going to take care of the restrictions here. So take a look at where we were here, where x has to be different than 0. So the variables were still in the denominator there, and y different than 0. Now, in the next question, we will deal with expressions with negative exponents. So let's take a look at how we're going to do this now. Now, first examine the expression. Check and see what we have. So what you have in here is the product of these two monomials. Okay, so they are monomials. And down here you have just another monomial, and we are dividing. Now, the first reaction sometimes, from what I notice in class when we practice and when we have discussion, is whenever we see negative exponents, people rush to turn them into positive. That should be our very last step. So converting exponents from negative to positive is our very last step. So we are going to multiply and simplify as much as we can, right, without worrying about the negative exponents yet. So here we have to apply the BEDMAS rule, as always. And remember that inside brackets, there is nothing you can simplify. So they're completely simplified in each set. There are no exponents applied outside the brackets, so there is nothing. So there is division and multiplication. They normally have the same order. And when we have rational expressions like this, what we do is to simplify the numerator, so multiply first. So we will multiply negative 6 by negative 9. And negative 6 times negative 9 is equal to a positive 63. Then we'll multiply x to the power of negative 2 by x to the power negative 5. So x to the power of negative 2 plus negative 5 is negative 7, x to negative 7. And lastly, we'll have x to the power of, y to the power of 1 with y to the power of negative 2. That will give y to the power negative 1. And down in the denominator, we have 3x squared, y negative 4. So next, we will perform the division because there is nothing to simplify up and down here. 63 divided by 3, that would be equal to 21. So these are taken care of. X to negative 7 by x to negative 2 is x to negative 7 minus 2. And y power negative 1 divided by y negative 4 is going to be negative 1 minus negative 4. And here is a small little miracle just happened. 21 x to the power negative 7, and y, here is the miracle. So y is to what power now? Negative or minus negative 4 is like plus 4. Negative 1 plus 4 is positive 4. So we don't even have to worry about y. One last step, we are going to convert the exponents that are negative into positive. And the way we do it is we keep whatever exponent is positive on top. 21 is also a numerator, so it will stay here. And the denominator will carry that negative exponent, will make it a positive. So one easy, practical, technical way of doing this is by making a fraction right here, writing 1, and then whatever is negative has to come down. Remember, coefficient is allowed to be negative. I've seen that happen. Don't make negative coefficient, numerical coefficients become positive by coming down. It doesn't work like that. So we're going to talk more about it in class as we practice. Now, very important that we state also the restrictions that x shouldn't be 0 and y shouldn't be 0, and you let the world know about it. And I would like you to try the next example in the exact same way. And you may find the notes posted online on our Brightspace classroom. And our next video will be about expressions with 0 and negative exponents. And I'd like to dedicate a separate video for this. Thank you for learning with me, and bye for now.